Our next speaker is Dr. Jinha Jung. He's with TAMU CC, and he's also this summer with AgriLife. So he's sort of like me in a way, but he's going to talk to us about high throughput phenotyping using UAS.
Is he AgriLife?
I told him, I said he's this summer he is.
Thank you.
So, go ahead and take it away.
Thank you. Thank you. So today I'm going to talk about high throughput phenotyping using UAS. So what do we mean by high throughput phenotyping? So basically, we want to measure crops in a very fine detail in a very quick short time period. And you're going to see a lot of overlap from my presentation with Michael Starks and Dr. Landivers. And I think that this is kind of a story that how much we are integrated together. We'll talk about similar things together. But my presentation is somewhere between Dr. Starks and Landivers. I'm trying to kind of bridge those to we integrate everything into one. So again, Dr. Stark talked about different types of UAVs, and usually we call and somebody called like a unmanned aerial vehicle, UAVs, and somebody called it UAS, unmanned aerial system. So what is different between those? Usually what I mean by drone and UAV, we talk flying platform itself, unmanned aerial vehicle and an aircraft without a human pilot on board. But what we mean by UAS aircraft system is not only UAV or drone itself, but we need to have ground control station so we can just control those UAV up in the air, and we need to have some kind of communication channel between those two. UAS is kind of more like a complete system where we're going to have more full control of this the drone up in the air. So why we want to use UAV? Dr. Stark already talked about it. Like it's going to be cheaper, it's going to be more accessible, it's going to be more easier and more efficient, and higher temporal resolution. What I mean by that, we can fly more frequently because the satellite images, it's going to have a global coverage, but in order for us to come back to the same location, it takes usually about more than 2 weeks to come back to the same location. But for UAV, we can fly as frequent as we want. Like if you want, we can fly every hour or something like that. And environmental friendly. What I mean by that is that we don't need to burn the fuel. We can use the electric motor to stay up in the air. Is less risk because there's no human on board. But there are some bad things about UAV as well, and they are more able to the weather. What I mean by that is we cannot fly on a windy day. We cannot fly when it's going to be more restricted in terms of weather condition, and limited flight time. When you have a big plane, you can fly much longer in hours. But when for talking about UAVs, usually especially for the multi-rotor platform, we're talking about like 20 to 30 minute extreme platform. And this is not the limitation, but the limitation of the legal restriction, because UAVs are usually only allowed to fly up to 400 feet. Of course, launch with this special permission, we can fly higher. But the most of the case, this 400 foot ceiling is going to be limited by this regulation. And payload as well, because when you have a big plane with heavier sensors, but we are limited by this payload of this UAV system. And less control in emergency. When Dr. Stark showed this picture, plane up in the trees. In case of the emergency, for the full scale airplane, there's a pilot on board. They're going to have more control for a longer period of time. But UAV, if you just crash, it's going to crash. So type of UAVs, the blimp. I think this has been around for a long time, and this is in type of UAV because there's no human on board. Of course, there might be human on board, blimp, up in the air, like this, and there's a kite. They can be considered as the type of UAV as well, and there can be helicopter platform, and these are the two different platforms that is kind of big players. One is fixed wing and rotor wing. And I think Dr. Stark already covered about what is good about the fixed wing and what is good about rotor wing. There is pros and cons within those two platforms. I'm not going to go over that. And this is another platform that is kind of getting more popular. We call it a VTOL system, vertical takeoff and landing. So this is a kind of combination of multi-rotor and a fixed wing. Fixed wing, you can just fly faster and cover bigger area, but they need a wider area to take off and land, because they have to kind of use some motion to take off and landing. So what they do is that they basically combine this multi-rotor so that when they take off and land, they're going to use these motors to take off and land. And once they, there's some turn off this engine, and they're going to turn on this, the front engine to, move forward with that. So component of UAVs, there's main engines over here. We call the flight controller. How they're going to fly. There's motors over here, ESCs, and batteries, GPS. This is a telemetry, those kind of stuff, which I'm not going to go over in detail. But we have this different kind of UAV component that is making this working. And another component that I want to mention is that this sensor integration. So we have all these different kind of sensors. We have RGB camera, multispectral, hyperspectral light, all those kind of stuff. We have a UAV, and a lot of people think that sensors and UAV, what we need to do is we just put them together and fly. And a lot of people task, but as a matter of fact, that is not a simple task, because we cannot just fly. We need to have fly in a very specific pattern to collect the data so that we can post-process it, and that also depending on what kind of sensor you're flying as well. Like just RGB camera and multispectral camera maybe can be operated in the same way, but hyperspectrally we call the push broom sensor. They have a line scanner so that their flying pattern might be different, and for the LiDAR their flying pattern might be different as well. So this is where in a sensor integration is going to be critical. We have a flight controller that I showed before. We have a different sensor over here. Then how we are gonna develop this flight controller can control these sensors. Up-in can collect the data that we can post-process it later. And this is where all this electrical system comes into play. And I'm lucky enough to work with smart student like the Luis Bonilla and Vincent. Daniel Gonzalez, he's not here because he's taking class today. But they are helping us to develop this kind of how we're gonna actually control sensors from up in the air. Another component is how we're gonna actually mount the camera, because camera with those sensors can be mounted looking down eventually. But this here is an example of mount system where we have a multispectral camera, resolution RGB camera here, and there is a lot of the mechanical engineering design aspect going in, how we're gonna actually isolate the vibration from the platform, because we're gonna having a very motors up in the air, and we just design this kind of system. Under this we have battery, and how we're gonna actually set the center of gravity so that it's gonna be not kind of tilted this way when you're flying like this. And there is another system where the sensor is kind of stabilized automatically up in there as well. So I'm going to just quickly go over the data collection, and we are going to go over this in detail in the afternoon. We're going to see two demonstrations in the afternoon. One is in a multi-rotor platform, which is called DJI Phantom 4 Pro, and Dr. Stark's group is going to do the demonstration of fixed wing platform. I think it's going to be EV. And basically, we're going to go over all the time. We go over this like checklist, because safety is the most important aspect of this. So there is a list of things that we are going to go through. And in addition to this, like Dr. Stark mentioned, the GPS on board on the UAV is not going to be accurate. So what we do is we do the GPS surveying of those ground control target. So we're going to show you that how we do those GPS survey in the afternoon as well. We go through this pre-flight checklist. We're going to do the mission planning, and we are not going to fly, because you're going to see that later in the afternoon that you're going to realize how difficult it is to fly manually. You think that this following this in a straight line is going to be a simple task, but as this one get away from you about 50 or 100 meter, you're going to lose orientation. You're going to lose a concept of am I flying straight north or in a slight northeast, northeast or northwest. It's going to be, it is a very, very difficult task to do it. And we're going to do this kind of mission plan. This is one example of open source project called the Mission Planner. But we are not going to be using it. We're going to use a smartphone app to do the mission planning. We're going to come up with this mission plan. What we're going to do is the autonomous flight We are not going to just, we are going to hold the flight controller just in case something happens. But what we do is just, simply press a button on our screen, that take off. Then it's going to take off. It's going to follow this, the flight path that we saw in the previous slide. It's going to collect the data while it's flying this pattern, and it's going to come back to home location, even do the landing automatically as well. So all you need to do is hold your remote just in case, press a button, it's going to take off, collect the data, come back to the landing. And 99%, that is all you need to do. But like you saw in the picture, Dr. Stark's presentation, emergency happens. And that's where those experienced pilots comes in when it comes of emergency or something weird happens. How you can just react quick enough so that you can recover the plane. Because I think I've been doing this mission for almost 3 years, and I have so many emergencies. And looking at it, I can tell, oh, there's something going on. And when you are in doubt, don't risk, just take it back. Make sure everything is working. And once we have this one, done the actual flight, what we're going to do is we're going to just download the data from the UAV and post-process it. Like I mentioned, we use different kind of software, Pix40 or PhotoScan. These are the commercial options. And OpenDrumMap is an open source. But based on my experience, OpenDrumMap works okay for static object, for the vegetation. This plant is always moving, and OpenDrumMap is not giving us good results. So we are kind of stick with this commercial option over there. For motion, like Mike explained, basically we have different images from different angles. We try to find the same point from this different camera and make it different in a bunch of triangles so that we can get the 3D measurement out of it. And when we collect the data from the UAV, this is the one that we're going to collect, RGB images, multispectral, thermal, and the LiDAR point cloud. We call this level 0 data product. The first data product we're going to collect it from the UAV. Then we just do the structure from motion from this raw data to generate this data product. Auto mosaic, like Dr. Stark mentioned, like stitch image together, move all these distortions so that we can do the measurement out of it. And we call the digital surface model, like said, this sensor is going to only see the surface, not this below canopy structure. And we're going to also get the 3D point cloud as well. It is using structural from motion. We have a bunch of overlap and go through this structure from motion process. Then we're going to get the auto mosaic images and digital surface model, and we're going to get the 3D point cloud as well. And once we get this level 1 data product, what we do is we further process it to get something like canopy height, canopy cover, canopy volume, NDVI, goodness index, all different measurement. So how we, and even based on this, we can even go up like in level 3. We can do the growth analysis, and we can also do the water stress analysis like that as well. So how do we measure the height? And like in Dr. Stark's approach, once there might be some environment where the ground elevation, and that's where we can do those filtering approach where we want to know what is non-ground point, then we do the interpolation. But times when we do the row crops, when we have more control, and what we can do is that we can fly the field before the planting, so that we can get the ground elevation before the plant goes up. So that's exactly how we do it. So let's say this is one example of it. Like whenever we do the photo, only see this blue line over here. We call the digital surface model. They're going to see the surface elevation, and we need in order for height measurement, what we need is line over here. And what we do is we do the flight before planting, so that we can get this ground elevation over here. And this is an example of digital surface model. And this is an example of the digital terrain model we call before planting. And simply we just do the subtraction from this from that will give us actual height information. This is an example where in a very flat area, so those measurement is not going to be that much different. But when you have like this kind of terrain variation, those the digital surface model and this canopy height model is going to be showing a dramatic difference. Once we have this one, we just, like I said, every time we do the flight, we're going to have this dot measurement, fit this growth model, and believe, and this is growth model, then we can just do the first derivation to get the rate and extract a different kind of information from this measurement. And another analysis that we do is in a canopy cover. Basically, when images, we just do we just want to know which one is crop, which one is non-crop, and basically we have this one. We do the classification so that we have all this white pixel is going to be the canopy, all this black one is going to be non-canopy. Then given area, we can just calculate how many white pixel versus how many black pixel we calculate, so that we can calculate canopy cover. And this bottom map is going to be representation of canopy cover. As you can see, we have more crops, we have a greener area, which means you have more canopy cover in that area. And good thing about this is that we can automate this process. And once we have the data collected, this is one example of cotton field in 2016, and we can run the software to calculate canopy cover whole area. And this is how it's going to look like. And this is the 1 week later, and we can just keep tracking of this canopy or the cotton growth over the season. And this is a little bit more zoomed in images of cotton in 2016. As you can see, we can see all these leaves, but all which is cotton flower. And we can also develop a program to counting those cotton flowers automatically. So you can see that all this in a white spot, program to tag them and count them. And we can just count how many flowers per square meter. And we can just create a map like this. And good thing about this is, like I mentioned before, every time we do the flight, we can get the measurement for the whole field. This is example of June 23rd, 2016, and 4 days later. And this is about a week later. So we can just keep tracking of how this cotton flower is progressing over the whole field. And I think Dr. Landvall or cotton physiologist is going to appreciate this. In the top layer cotton flower is going to be indication of a cutout, I believe. And and we can get the timing of cutout for this different varieties very. And this is the same area that as you saw before, and this is in the middle of season. And but a lot of times we don't care about this middle of season. What we care about this cotton is, and at the end of season we are cotton in the fiber. And this is how it is going to look like at the end of season. As you can see, all you carry is those white spot. Let me just go back here. And you're going to see that some of this area here, we don't have much cotton over here, but when you look at in the middle of season, they don't look that much different. But what you can do is that we can also write a program to detect those white cotton balls and do the classification, and we just tag them, count them, how many, measure how big those cotton balls are, that we can create a map like this, how much cotton ball we have in each square meter, and we can use this information for later analysis. And this is one example of thermal imaging. We have green cotton and red cotton area over here, and we can measure the surface temperature over here, and the blue color means cooler, red color means hotter. As you can see that green cotton over here is cooler than red cotton, as you can expect. And we just have this grid structure that you have. Then the final data product we're going to do, drive is going to be these kind of numbers, so that research scientists can use this information to do the further analysis. And you're going to see the presentation from Dr. Murilo Maeda, where he's going to talk about how we are using this to do the further analysis. And he's going to also talk about the hub, the infrastructure where we are doing the active communication between computer scientists, engineers, and agriculture scientists. With that, I think I'm going to stop here.
Can you comment about your recent flights over the cropping systems, plots? Dr. Roper will be interested in
Oh, yeah. I think maybe Dr. Maeda can show some of the real example. There we have. You're talking about the annex.
the no-till.
Yeah. So we are doing this year doing flight over the till and no-till over flight, and we are finding out very distinct difference between till and no-till in terms of the height, in terms of the sorghum head counting. So we are seeing very distinct difference between tail and no-tail. We know that no-tail is better than tail, but a lot of people, I think we think we can show statistically that no-tail is going to give you better yield at the end of the season, and hopefully that Morello can show in a real example later.
But that's a rule